Terrible. All right, so what we're talking about in chapter 26 is DC circuits, by which we mean direct current circuits, which essentially means the current will be traveling the same direction and magnitude the entire time. So to contrast that with AC or alternating current circuits, in which the magnitude and the direction is sort of ever-changing. Direct current is the easier version of the two types of circuits. The current sets itself up in one direction, and that's just what you have for the entirety of the circuit that you're analyzing. So really quickly, mostly as means of a review, we have there on the left some circuit elements and the symbols we're going to use for those as we work through different circuit diagrams. The battery we're used to, the capacitor we already learned about, the resistor we talked about a couple of weeks ago in that quick chapter we had right before spring break. We know about that. Wires, just lines, will typically have negligible resistance, but keep in mind, even a wire, it still has some resistance. It's not perfect. And especially if I have a lot of wire with current passing through it, that little bit of resistance tends to add up and become more and more significant, okay? Most of the time, though, we're going to pretend that that resistance is negligible. We're going to incorporate switches from time to time, which will represent with just a little break in the wire, and we'll imagine that that little break can be moved back down and reconnect the circuit and give ourselves a complete path once again. And I think we briefly spoke about ground at some point a couple of chapters ago. Yes, I see some thumbs up. Sometimes I get confused between 7B and 8B, which I'm simultaneously teaching, and we're like, because the topics are covered, we're like a month off from each other. So sometimes it's like, yeah, what did we talk about, and in what depth, and what happened when? So things get a little confusing. Ground we talked about, there's a couple of symbols for that as well. Really quickly, before we get into circuits, we have in the bottom right, I guess a battery. More just looks like a box with a couple of terminals on top making a connection. This terminal voltage, V sub AB, the potential difference between the two metallic connections on a battery that we connect to the rest of the circuit, is not as simple perhaps as just that, okay? The terminal voltage we assume is going to be, well, the output potential difference, how much potential difference it's supplying to a circuit. This is only true, however, if the current is zero. So if there is no current, this potential difference between the two connectors on the battery, we can say, is equal to the electromotive force, the amount of potential difference that's supposed to be supplied by that battery. I think we also discussed the idea that electromotive force is a misnomer. It's not really a force. It just means potential difference. It's just a fancy, old-fashioned term for the exact same thing. Okay? So you might imagine, like, okay, you buy a battery. The battery on it says 12 volts. You've been to the store to buy a battery at some point, right? Maybe it didn't say 12 volts. Maybe it did. And maybe you were very happy about your new battery. You're like, I want 12 volts of potential difference. This is going to be fantastic. I'm going to take it home and connect it to my circuit. And when I make measurements in my little lair at home or laboratory or whatever, a few of you laugh because you have one, don't you? You have a lair where you do experiments, and now I'm a little scared. I'm going to keep moving this direction a little bit, all right? You expect it to give you 12 volts, what's on the packaging. Well, that is a measurement of the electromotive force, what it's supposed to put out if there is no current passing through the circuit. Well, no current passing through the circuit isn't terribly useful, right? I need to connect it to something, and I need that potential difference to cause electrons to flow, and then I have current flowing around through the circuit, in which case, at some point when I make a connection over here to circuit elements, which may include some resistance, there's going to be current going around this loop and at some point actually passing through the battery itself in order for it to be part of the complete loop. Well, you may remember the battery has a bunch of stuff in there, right? There's the electrolyte that has to be part of that current loop. It does not have zero resistance. It may have very low resistance, but as soon as I start passing current through the battery, there's going to be some opposition, which we represent with this little r and a diagram of a resistor there. So keep in mind, that's just a schematic. There's not actually a resistor in the battery itself, but it's just representing the internal resistance of the battery. So we can say that internal resistance, R, is not equal to 0. There is some there. Most of the time, we can even treat it as negligible, but it is going to use up some of our potential difference. So what we can add to this, we could say that if the current is not equal to 0, this terminal voltage is going to be somewhat less than the supposed electromotive force being supplied by the battery. We're going to lose a little bit. As soon as we make a measurement in a circuit and pass current through it, all of a sudden maybe you get a little angry at the person who sold you the 12-volt battery because now it says 11.97. And you're very particular about such things. You're like, 12 volts. I wanted 12 volts. Why did they sell me 11.97? Well, they didn't. They sold you 12. But as soon as you use it, the internal resistance uses up a little bit of that resistance. So we might say something like this as well. We could say that the terminal voltage is equal to the electromotive force minus the potential difference that gets used up by the internal resistance, which is going to be the current times that little bit of internal resistance. However, I say all this just to tell you that this happens. For the most part, when analyzing a circuit, if it tells you V is the potential difference for the battery, that's just what it is. We're going to ignore the internal resistance unless a problem specifically says to include it. So we will say, for most problems, assume this little r is negligible. Okay? Batteries have internal resistance, so while they try to provide a particular potential difference, it's always going to be a little bit less. Good so far? That's easy, right? Yeah? We should just stop right there and be like, exam 3 over this one slide. That'd be too easy. Question back here first. It's continually taken away. As long as there is current passing, the potential difference that's supplied is a little bit less. Okay? Question down front. What's that? I forgot the E where. Assume. Yeah, I kind of. I don't know. Zoom in on that. Oh, hold on. I've got an E there. You know, see, this, hold on. We can, this is the M. Like that. And this is the E. No, you're not buying that? It kind of works. Okay, I agree. Thank you. I'll try to fix this a little bit. Maybe we can like Did that make it any better? See if we get rid of the, oh, now everything is terrible. Whoa. We'll get rid of that. Now we're just drawing. Now I lost part of some other letter. What was that one? U. M. There, that's kind of assume. Hey, that looks much better. Great, thank you. Sad. By the way, I often sign my last name kind of like this. You know, it just kind of dies at the end. It has an L, and that's about all there is to it. You do that as well, right? No? You're like, you don't sign my last name, so I hope you don't do that as well. It's funny, like looking back when you were a child and the first few times you had to sign your name. You know, it's like let's make this thing look perfect. And now it's just like, bleh. Like, who in the world cares anymore? All right, let's talk about some circuits. Series and parallel resistors. So the idea of series and parallel, that's going to be consistent with exactly what we talked about with capacitors. But the rules of how we combine resistors is going to be different than what happened with the capacitors. So series, again, is just one right after the other. I'm not going to write all that out again because you have it back on the slides about capacitors. Series just means one right after the other. So if there is no break in the circuit and one resistor is connected directly to a second resistor and then maybe to a third, a fourth, and a fifth, and a sixth, and a seventh, well, the same current, whatever it happens to be, is forced to pass through all of the resistors. So we could say that all resistors in series have the same current passing through them. All resistors in series have the same current. However, they may have different voltage or potential difference. What is that word I just wrote? You know, sometimes it's hard to talk and write at the same time. You just get lost. There's a little hiccup, and you write words like potential or something or other. I don't know. Oh, let's go back a few. TIAL should work. Potential. There we go. Difference. Why potential difference being different? Well, they have potentially different amounts of resistance, right? And also, they're not connected such that they share the same conductor on one side and the other side like things in parallel do. So you'll notice in the diagram at the top right, we have a resistor 1, a resistor 2, and a resistor 3 in series with each other, and they also have different potential differences associated with them because I'm talking about the potential difference from one side of the resistor over to the other, and then from that side over to the other side, and from this side over to the last. All of those potential differences have to add up to the total, to what's being produced by the battery, because, well, the battery connects all the way from one side to the final side of that third resistor. So we could say that the total potential difference, V in the circuit, is equal to the potential difference across resistor 1 plus that across resistor 2 plus that across resistor 3. Or we could have that for just 2 in series or as many as we possibly had in series. The same exact equation might apply. But since they have the same current, I could use Ohm's law to write I times R1 for that first potential difference plus I times R2 plus I times R3. No subscript on the I because it's the same for all of them. And then we could factor out that I. And again, this is for the entire circuit that we're dealing with. The total overall potential difference is equal to the total current, which is passing through everything, times the sum of these resistances. So I might say that this sum of resistances is my equivalent resistance for the circuit. If they are in series, the equivalent resistance is simply the sum of all those resistors, for as many as you may happen to have. Which I think makes some logical sense, right? You can imagine if resistors are providing opposition, and maybe I'm an electron that's trying to pass through these resistors one right after the other. Well, I try to get through the other one, and it opposes me. So you might imagine me in there like bouncing around. It's like, oh, I have to fight my way through the resistor. There's some resistance. And it's like, oh, dang it, another resistor? And you fight your way through that. That's more resistance. And then you have to fight your way through the third one. And you have no choice but to go through all of them. But it makes sense that whatever the total resistance is just going to be the sum of all of them. Okay? Anybody have any questions? Straightforward? Easy? Am I true to my word so far today? Uh-huh. Have you fallen asleep yet? Uh-huh. A few of you. That's okay. I should make it my goal one day to see how many people I can put to sleep in an hour and 20 minutes. Nah, I don't know. Maybe it's a good idea, maybe it's not. Who in the world knows? So take a look at this and tell me the answer as soon as you have it. There's a lot of these type of questions today, so we'll need to try to do them somewhat quickly. 3 resistors in series, there's 9 volts being supplied. What is the potential difference across each resistor if they are identical? And I think that's relatively straightforward, right? Should be 3 volts across each. If they're the same resistance, whatever the individual potential differences are, they have to add to 9. So if there's individual different resistors, then there'll be a different combination of potential differences, but it's still going to have to add to 9. What about this? What is the voltage across R1? In other words, it's asking about V1. Vote when you have it. I think I see some happy answers out there. They were a little slower coming that time. Yeah, maybe. I'm going to do this sort of the long way, if that's okay. I could say that the equivalent resistance here is 6 ohms, right? Because we're just adding those two together, which means I could say that the current is 12 divided by 6, or 2 amps, and then I could use that current, which is passing through everything. 2 amps is passing through everything in the circuit, and use Ohm's law individually for each individual resistor. And I could say that V1 is going to be 2 times 4, which is 8 volts. And, of course, the other one is going to come out to give me 4. So V2 is 2 times 2, which is 4 volts. And you can see that the 4 and the 8 add to give me 12. So everything sort of works together. Keep in mind, when using Ohm's law, we can use it for the entire circuit, or we can use it for individual resistors, or even individual like segments of the circuit itself. We just have to make sure that we're using a consistent V, I, and R that are applying to the same thing, okay? And we'll see that a little bit more as we work through some more complicated circuits. Resistors in parallel. Anything you want to say or ask about series so far? No? Are you sure? Yeah? All right, resistors in parallel. Resistors in parallel, same thing as before. We know they have to have the same potential difference across them if they're in parallel. So we can start with that. We could say that V is the same for any resistors in parallel, just like we had with capacitors, because they all share essentially the same conductor or same equipotential surface on one side and the same one on the opposite side. So V is the same for all of these, but in contrast, they may have different current passing through them. Same potential may have different current, or I. So if I take a look at this circuit on the top right, let's just follow the current. Let's say it starts from the positive side of the battery and is working its way around clockwise. It gets to this point A, where all of a sudden the circuit splits. You can imagine now that, well, any individual electron sort of has a choice at that point. It's not going to split in 3 parts and sort of go all ways, but it's going to go down one of these 3 branches. If I consider all of the current, it gets to that point, and, well, some of the electrons go down one, and some go down the other, and some go down the other path, really depending on how much resistance there is down each of those 3 paths. It'll be proportional to those resistances. So we could say that the total current in the circuit, the current, if you want to think of it, that is all put together and leaves the battery or passes through the battery, is equal to the sum of these currents down the individual branches. There's a conservation of charge there that's in effect. Whatever total current I have has to equal the sum of the individual branches, and then you can see at point B, they all come back together to give me that total once again. We can go with this and use Ohm's law and say that that total current is the total potential difference over the equivalent resistance. So everything there on the left is talking about the entire circuit, and on the right, we're breaking it down into individual components of the circuit. So I'm going to use Ohm's law for each part of this as well. This is V over R1, and this is V over R2, and this is V over R3. No subscripts on the V because it's the same. The total potential difference is being applied to all 3 resistors. And then something kind of nice happens. All these V's cancel out. That is the official sound of things canceling out, by the way. Don't you think it should be? I can imagine then as you're taking an exam or something, there's just across the room, as you cancel things out. And I should write the test based on how much noise I want, right? If there's a lot of things to cancel out or just a little, and if you don't make the noise, you lose points, and that'd be I can't do this. I don't know how to implement this exam. So notice what happens here. 1 over REQ equals 1 over R1 plus 1 over R2 plus 1 over R3, and that would continue for as many as you have in parallel with each other. So the rule for parallel resistors is like the rule we had for series capacitors. It's just flip-flopped, and you have to keep that difference straight, okay? Let's see. Is there anything that I wanted to add to that? A couple of different things here. Something I didn't say there and something I didn't say here. Okay, so I'm going to use this next slide where it points out we can obviously have circuits that kind of combine these 2 effects, and we're going to do an example here in a little bit where we have a mixed parallel and series circuit just to make sure we're all on the same page and know how to solve that. But I would like to add a little bit more detail to both series and parallel and kind of contrast how they work, just to give you a little bit more, conceptual or intuitive idea of as far as what's happening in those circuits. So I could redraw these circuits like in series to represent what's happening to the potential as I move through the circuit. So keep in mind, when we draw circuits like this, we always draw them typically kind of neat and in an obvious way that shows me what's in series and what's in parallel. But if you were really building a circuit, you'd have wires all over the place, right? Nothing's going to be parallel to anything else geometrically. And series things, like you probably have to like pull wires out and be like, what's connected where? This is a mess. It doesn't change the fact that something's in series or something's in parallel based on how it's wired. So I could redraw these circuits that we've already had and kind of twist things around a little bit to help represent something that I think is instructive without really changing the nature of the circuit itself. So I'm going to make the battery we had before vertical, since potential is analogous to height when we're talking about gravity. And we're going to pretend that as we go across the battery, essentially we're going to a higher potential. So let's say that this is our ground level, and this provides some positive potential difference as I go higher in the circuit. That means that by the time I go all the way around the circuit, I need to be back at zero. It has to use up, if you want to think about it that way, all of the potential difference, because by the time I get back to this bottom part of the battery, we're back at zero level. So I have to go from this high point all the way back to the low point again. The way we do that is by traversing each of those resistors. So maybe we have a resistor 1 here, and then maybe we have something here that's resistor 2, and let's make it ever so slightly shorter, just because, well, these are not necessarily the same. And then maybe resistor 3 has a lot of resistance. So R1, R2, and R3, and then I'm going to connect that back to the beginning. So you can think of each one of these potential changes as you go across the resistor as a drop in the potential at that location. So these are often referred to as voltage drops. More of a, I don't know, just lingo that actually refers to something that's physically happening. Like the top of that resistor 1, you're at a certain potential, and when I get to the other side of it, the potential at that location in the wire is lower. The voltage has dropped. I like to think of it as sort of like the current was just like a waterfall, right? It was at one level of height, and it went through the resistor, it fell some, and now it's at a lower level, and it's going to fall through another resistor, and the voltage is going to drop once again. So that's going to be voltage drop V1, and this one will be voltage drop V2, and this one will be voltage drop V3. And it's pretty easy to just look at that diagram and say, oh, V is the sum of all the individual voltages or potential differences. It agrees with the equation we had. Simultaneously, it's pretty easy to see that the current really has no choice, right? It's just going to go through this one, and then this one, and then this one, and then back to the start. It never changes amount. The same amount goes through each resistor or each waterfall with air quotes, okay? Series circuits. Let me redraw the parallel circuit as well. The parallel circuit, and we're going to use this height metaphor once again. So we'll go up to this level. We'll say down here is V equals 0. And now we're going to just draw all the resistors like this. And we'll say that it really doesn't matter what the individual resistances are. You can see that for all three, the height change, the voltage drop, the voltage change is exactly the same. So we could write that as equals V1 equals V2 equals V3. Doesn't change for all of them. However, different amounts of current could potentially go down these branches before coming back together, all into one, to go back through the battery once again. Questions, thoughts, complaints, compliments, condiments, coffee? I don't know how those slipped in. I'm sorry. I'm just thinking of things that start with a hard k sound, apparently. Let me add to this one more thing. And if this confuses you, please forget I said it. Okay? Can you agree to do that? If it helps and kind of ties a couple of things together, then by all means remember it. It's up to you to determine which one. So we had this equation, you might remember. Resistance is related to resistivity times length over area of the material that the current's passing through. You remember this, right? It's only been like 20 days or something. I don't know last time we actually had class and talked about this stuff. Okay? In this one equation, I also see series and parallel resistances, if you think about it just a little bit further. Okay? The top. If I add more length of material that current has to pass through, I get more resistance. In other words, if I connect more resistors after each other, I'm essentially increasing the length of the resistor. It's kind of the exact same thing, right? So this represents a series combination. More length of resistance or more resistors in series gives me more resistance, okay? The area, the cross-sectional area, I see as representing parallel resistors. Cross-sectional area. If all of a sudden I give a wider path for the current to pass through, well, this says the resistance will go down. It's easier for the current to flow. Well, if you think about it, parallel resistors is like, oh, you don't have to just go through this resistor. You can also go through this one. If those are the exact same resistance, I just doubled the cross-sectional area for the flow to go through. If I put a third one in parallel, there's even more places where the current can flow. It's almost like on a highway, if like all the lanes are blocked but one, all right, the traffic can't flow, you just open up another lane, things can flow more easily because there's less resistance, there's less opposition, okay? I don't know. Maybe that's helpful, maybe that's not. Take it for whatever you want to, okay? Let's see. Let's move along and see if we can solve a few more of these relatively simple circuits. The current through resistor 1. Please don't think too long. Got it? I hope. The potential difference across both of these, V1 and V2, is also 10 volts, right? So I can, for resistor 1, say V1 over R1 equals I1. So that's just 10 over 5, which gives me 2 amps. 2 amps for the current through resistor 1. So our answer there is 4, okay? Everybody okay with that, maybe? What's happening here? Here we have parallel resistors with an ellipsis to indicate we're just going to add more and more and more resistors in parallel. What happens to the current, the total current in the circuit, if I increase the number of resistors in parallel? I'm seeing some votes for increases. Why? What's happening to the overall resistance? It's going down, right? So we could say that REQ is decreasing. More in parallel decreases the resistance because we're opening up more lanes, which means that the current in the circuit will increase because there's less opposition. What is next here? That's a beautiful light bulb. I wish I had a few of those in my house. That is just really nice. Look at that. Wow. The closer you look at it, it looks kind of like a little creature now with kind of a undefined face with 2 legs. So we are assuming here that essentially wires have no resistance. At least it's very, 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 very low compared to the resistance that a light bulb would offer. So basically, all of the current is going to go through the wire. It's going to go around this way. You could think of this as 2 things in parallel. A resistor, which is the light bulb, and then basically no resistance in parallel with it. Okay? As that wire approaches 0 resistance, more and more of the current is going to go that way. If we assume that that's 0 resistance, then basically all of the current is going to go that way. This is what is commonly referred to as a short circuit because we essentially gave the the current a shortcut. Like it's like, ooh, I don't have to go through the light bulb? Well, why would I bother? I think I'm just going to take the path of least resistance, to quote a common phrase, all right? What else do we have here? I like these answers. It's 5. Moving along. Okay. It should be 5. One of these weird answers should be the correct one at least once. I think we're starting to get to the correct answer. It's going to glow brighter, but why? What's happened to the resistance in the circuit, first of all? It's decreased. So Req has gone down, which means I has gone up, which means, I don't know, let's just call this brightness has also gone up. Okay? We're going to see on these upcoming slides that brightness can be directly connected with our power equations in circuits. More power is going to indicate more brightness. So you might remember power is I squared R. So for a given resistance, if I increase the current through it, there's more power output, which will be reflected in the brightness of the bulb. Let's see. So what can you deduce about these two options? Hello. How are you? Oh, did I make you drop your phone? Because if I did, I'm sorry. I hope it's not broken or anything. It's shocking how well phones survive these days. Unless you're my wife's phone. Yeah, it doesn't survive very well. You know, there was one morning where my wife dropped her phone twice onto the floor before getting out of bed. I thought that was impressive, you know? Not walking around, not doing anything, just like, blah, there it goes. Off to the, alas, it survived. What do you think? 1, 2, 3, or 4? Ooh, I see some disagreements out there. Which one has less resistance? Yeah, you could probably just think of these as use the equivalent resistance for both and use that to calculate the power. This one has lower overall resistance, or REQ. It's going to end up producing more power. If you want to just make up some numbers, you should be able to calculate that there's a higher power output. Therefore, you're going to end up with more brightness, okay? Which you actually get to do a little bit here. You can do the calculations and actually use the numbers to find out exactly what the difference in brightness is. I'll give you a moment, and I'll shut up for a moment. Wake up. Go to sleep. You can try that as well. All right, let's do this calculation. You should have come to number 4, if all is well. Notice there is a 10-volt potential difference across this one, which if we were to calculate the power for A using I squared R, Yay. I think we're back. Good. Thank you. All right. What's our answer here? 1, 2, or 3? Should be 1. Why is it 1? Well, if I add that other resistor in parallel, then we could say that REQ for that parallel combination has now gone down, if you want to think about it that way. So there's less potential difference that's being used by that combination of resistors, which means that V1 will have to go up to accommodate because V has to stay the same. So based on that, what happens in this case? Notice it's asking now about the voltage across resistor 4 instead of resistor 1. Here comes someone. You think it's a trick question? Why? You think there's an answer 4 here? You lose. I don't know. No, that's not good. That potential difference, or the voltage across resistor 4, should decrease. Okay? If I add more and more resistors in parallel there at the end of the circuit, they're going to have less and less of a potential drop across them because their equivalent resistance is going down. R1 will be accounting for more of the voltage drop, and that latter part will be accounting for less. All right? And then I'm going to do one more of these, and then there's a few there that I'd like to skip. But I just like this question. It's kind of fun for some reason. You're like, you have a strange version of fun. I understand. Some of you look a little uncertain. You look very confident in your answer. So you're like, I'm confident, I think.
Yeah.
I don't think that's confident anymore. You think the answer is 4 or it's resistor 4?
No, it's a resistor 5.
It's resistor 5, number 4. That's not confusing at all. So you were looking for a trick question? Here's why. I'm actually joking. I noticed this when I put the slide up just a moment ago. I was like, technically, there's no connection here. They don't get any current. Nothing's going to happen. That's not what the answer is supposed to be. I'm sorry. That's a little mean. So from now on, when you have an exam, I suggest bringing a magnifying glass. You need to examine all circuits really closely for little gaps like that. So let's see. If R1 and R2, all these resistors are equal. So once we get to that first branch, the current should split equally. Okay, so they get the same amount of current. But once we get to the second branching, after the currents come back together, well, there's more resistance at the top than there is at the bottom, which means more current will pass through the bottom, which means there's going to be more current through R5 than any of the other resistors. Good job. Okay, although I like the other answer better. Are there any other little tricky things in here? I don't know what's going on with the wire right there. That seems a little odd. Ooh, up top, yeah, there's issues everywhere here. Oh, look at that. Oh, there it is again. This is a broken circuit, no matter how you look at it. Let's get rid of a couple of those. All right. Let's see. I'm going to get rid of that one. I'm going to get rid of that one. And I don't really care about space heaters, which brings us to an example problem. All right. 2:56 it is. We've got 34 minutes left. Are you okay? Can you survive the remainder of this class? Do we need a game? Do you want me to just stop talking? That's mean. That was a little too fast. You're like already smiling, like please, just shut up, all right? Before we do this example, I've got a new idea for lecturing. I don't think I can do it, but it would amuse me greatly, and I'm pretty sure I could set the record for how many I put to sleep. See, over the spring break, what is that? I don't know, I can't talk right. My wife and I decided, like, we need to watch something. She was on vacation at the exact same time. That worked out quite well. So we're like, we're going to watch. So let's watch all the Harry Potter movies again. Like, we've never seen them together, even though we've seen them individually at some point. So we're like, all the Harry Potter movies, we can do this. We've now completed this task. We didn't quite finish over spring break. We finished last night, actually. We enjoyed it. We had a good time. But I got to say, I am very impressed with the speaking style of Professor Snape. Just over every time the man spoke this time. It didn't get me like it did the first time. Just the way he could draw out a phrase and wait just like a little bit longer than you ever thought anyone would wait to say that next word. You remember this, yes? Like, just amazingly. I think I should talk like that going forward. You will fall asleep, won't you? Won't you? Yeah, a lot of that. I don't think I could handle it. And I need a darkness about me as well. And maybe a wand. Wait a minute. Maybe I'm a little closer than I thought. I don't know. Let's see. What is left in this lecture? Do you all hate Harry Potter, just in general? No? Who's pro Harry Potter? Who just hates it? No one hates it. Oh, a little hatred back there? Yeah? Okay. Who's ambivalent? Okay, ambivalent people. What should I have watched over break? I needed something to fill the whole break. Star Wars? Yeah, we need to do that as well. What? New movie Us. That's just one movie. That's not going to last over spring break. I needed more. Fear? Oh, it's really? There will be fear? Who else has seen that? Yeah? It should be seen? And I will be scared? We should watch it here? I will have to steal it, because I don't think that's going to work right now. So Star Wars, that clearly I need to go back and watch all of those. Lord of the Rings? No. Yes? No. Why? Not long enough. If you include the Hobbit movies, yeah, we could probably, yes. No to the Hobbit trilogy. Is there something I'm missing? Because it seems like it's either, Harry Potter, Lord of the Rings, or Star Wars. Is there like a massive movie sequence I've forgotten? Ooh. No. I don't think I can. No. What's back there? That's what we just heard down front here. The entire thing, huh? Whew. Yeah, I think I've seen them all already, but how many hours are we talking there? Does anybody know? 60? Ooh. I've never seen one of those. Pirates of the Caribbean? No, there's really too many of those. I saw maybe the first two, and then after that, it just, like, no more. What? Yes. There's 4? No. I'm not ever sure I saw the third one. I think I might have quit after 2, but the first one was fantastic. See, now you're all interested in things, aren't you? Can't interest you with series and parallel resistors, but we start talking about movies, and that's what happens. Come on. If you think about it, this is a movie of the workings of nature. I can't sell this. What am I trying to say? I can try as much as I want to, but I know most of you would like to just move on to your more advanced classes and be like, why do I have to take, the intro physics? Because you want to take, what do you want to take? A nap. Believe me, I do too. Badly. I very much need a nap. I haven't had one this week. Have I? Now I don't remember. I do need a nap. If you can't remember if you've taken a nap, you need a nap. There. You can write that on something. And that's a terrible rule. So here's what I'm going to do. I want to jump over and talk about Kirchhoff's rules, because I like them. We might come back to this example, but I just don't want to do it today. We've talked enough about just like straight up series and parallel resistors that I just don't think I can anymore at this point. Unless like the majority of you are like, do the example, I need it bad. Vote. Who wants it? 2, 3. Okay, we will come back and do it, but I don't want to right now. I want to talk about something new. Sound good? Marvel Cinematic Universe. I do think that sounds like a good time overall. Whew, that is long, though. Okay, anyway, Kirchhoff's rules. First of all, I have to confess something. I learned this as Kirchhoff back when and since then I've heard it pronounced at least you two? Like at least 2 other ways. So I've heard Kirchhoff and just Kirchhoff, and there's probably just a real pronunciation that I'm just not capable of as a human being because I'm sad. Does anyone have a 4th pronunciation that you think should be used? That just sounds like I'm removing cake from something, and that makes me sad. Cake is good. Cake off. We could. Maybe I'll just call it Kirchhoff, Kirchhoff, Kirchhoff. I'll say all 3 every single time I say the word. That won't annoy anybody at all right? So these 2 rules are, well, at least the first one is straightforward, the junction rule. This is essentially conservation of charge, and we talked about it really when we were talking about parallel circuits. If it splits and goes a couple of different ways, that has to come back together at some point and have the exact same amount of current. So if we look at a junction somewhere in a circuit, or maybe sometimes you hear this referred to as a node in the circuit, same exact thing, different terminology depending on textbook and professor. Any breaking point in a circuit, whatever current enters that breaking point has to be the exact same amount that exits that breaking point. So you can see they've labeled a current I1, I2, and I3. And you can imagine I1 enters this junction at point A and splits into the 2 currents, I2 and I3. There's no current lost. There's not like a hole in the circuit where some of it leaks out. That'd be weird, I guess, and not going to happen. And then later on, if we were to draw another junction here at the bottom, junction B perhaps, well, those 2 currents have to come back together and form the original current once again. So for each one of these junctions, I could write the exact same equation and say that I1 has to equal I2 plus I3. So you get one unique equation for 2 junctions in this case. All right? So for every 2 junctions, you're going to get a unique equation. That's the easy rule. The other one is the one that, I don't know, once you get it, it's not bad, but it tends to mix up a few people along the way, and that is the loop rule, which is basically conservation of energy. What we're saying with the loop rule is that if we think of potential, again, as height, if I go around a loop of any type in the circuit, when I get back to where I started, I have to be back at the same height. It would be really, really strange if I made a loop physically around the classroom and I went up the stairs here, I increased my height, and then went across back there and stayed at the same height, and then came back down the stairs, and then came back to this point, but when I got back to this point, I find myself 3 feet off the ground. How did that occur, right? Physically, that's just weird and impossible and just can't occur, okay? Same thing is happening with potential differences in a circuit. If I add up all of the changes in potential difference as I go around any loop in the circuit and go back to the exact same point, the net change has to be 0 because I have to end up at the exact same height, okay? So you can see that represented, well, if you wanted to, with this diagram down here where they've labeled points A, B, C, D, and E in the circuit. And, wow, look at where you have D, E, A, B, C, D. I'm confused already. So we're starting at this point, and then we go to here. And then we're going to work our way around the circuit and get back to point D. Well, you can see once we get back to point D, we're back at 0 because all of the increases and all of the decreases have to get me back to the exact same point. Okay? So how are we going to do this? And I need to skip forward a couple of slides just to kind of see how I've decided to put this in the slides because I forgot to flip through these before the start of class today, and now I kind of see what's happening. All right? So if we look at the circuit, you will notice there are multiple loops within the circuit that I could use to analyze the circuit. I need to point out that when I talk about loops, this is completely disconnected from what the current is doing. We're not like following the current. We're not like putting ourselves in the river of current and just see where it takes us. We're not swimming against the current like salmon. Like none of that's happening. Instead, it's more like we're floating above the circuit doing analysis. We're looking at what's happening in the circuit. And the loop is just the direction of analysis. I'm starting at one point and I'm going to analyze the circuit around an arbitrary loop back to the exact same point again. So you'll see that they've denoted 3 different loops in the circuit at the top. So here on the bottom right, they decided to go clockwise, just sort of around the left box. And then they decided another loop could be going clockwise around the right box, or maybe we could just go all the way around the entire thing. Those are kind of obvious ways I could traverse a loop in the circuit and arrive at the same point again. But don't forget, it really doesn't matter as long as I end up at the same place. If you really wanted to be a little more adventurous, like we could, I don't know, go around like this, and you could get back at the exact same point. The sum has to equal 0 no matter what I do. Or you could just like cause extra work for yourself and be like, I think I will go around it 4 times. And I'm going to go through there once, and then I don't even know where I started now. Does anybody remember? Bottom left, I think it was, and then go back to the starting point. A loop is a loop as long as it ends up at the exact same point. Once again, please don't draw that in your notes. That needs to go away. Bye-bye. Okay? So loops are the direction of analysis. So how are we going to approach Kirchhoff's loop rule as we analyze circuits? Actually, how are we going to handle both of these rules? So what I want to do is look through this sort of sequence of events and simultaneously work a problem on the next slide. I think that once we complete this, that'll be the perfect stopping point for the day. So let me draw a circuit that I'd like to use. I'm sorry that it's not already there, but just bear with me for a moment while we draw it. Let's see, something like this. We're going to put a resistor there, and we're going to go down and make a full box. Actually, let's put a resistor here and one there. Don't you love my resistors? They're very artistic, I think. You're like, no, they're not. They're ugly, and I hate them. Nobody? Okay, it's just me. I think they're ugly, and I hate them, but they get the job done. And also, I have a little issue with my circuit over here. So let me see if I can fix that somewhat. Whee! There is actually nothing over there. Let's put a middle branch here. We're going to put a battery there, and a resistor, and another resistor, and I think I've included everything. Okay. And then I'm going to give you some values for these. We'll say that this is a 30 ohm resistor. I'm going to leave the units off just to make it a little cleaner. That one's 40. This one's 1. This will be a 45 volt battery. This is a 1 ohm resistor. This one is 20. And this one is 80 volts. You got it? Did you draw it? Is it beautiful? Did you draw it neater than I did? Did anybody use a straight edge? Did anybody use tools on your tablet to make straight lines? I thought so, yeah. I just don't care enough. I'm sad. So once we have the circuit, let me go back a slide, if that's okay, just to look at the first thing in this list that we're going to do. Label the current in each branch of the circuit and assume a direction for the current. Unless the problem tells you the current's going a certain direction and has a certain value or whatever, or has maybe a certain symbol applied to a certain branch of the circuit, you get to just make it up. And it may not be obvious at first which directions the current is traveling, and also it doesn't matter. If you pick the wrong direction for a current, you'll end up getting a negative answer for the current, and you'll just be like, oh, it was traveling the opposite way, no big deal. The math will save you. So we could look at this and assign current names in any direction we want and give them any name we want, okay? So here's what I'm going to do. I'm going to say that around the top, going this way, I'm going to call that I1. And we're going to say that down around this way, I'm going to call that I2. And through the middle, I'm going to call that I3. Totally arbitrary which one is 1, 2, and 3, and whether it was clockwise, counterclockwise, or left or right. You can even draw directions of current that seem completely counterintuitive. Like, it seems like it would go that way, but it just doesn't matter. So let's see. After we have that, number 2, apply the junction rule to each junction that yields a different equation. Well, we only have 2 junctions here, and they're both going to yield the exact same equation. If I look here at the left, we could say that I3 is going to be equal to I1 plus I2. That is one equation that we can use in this particular problem. Yay, junction rule, easy and done. You'll notice we have the values for both batteries, all resistors. The only thing I don't know is all 3 currents. So there are 3 unknowns in this problem, which of course means I'm going to need 3 distinct equations. We could generate many more equations than that. We could generate a variety of different equations. We just need 3 to be able to solve the problem. If we go back over to the previous slide, number 3 is applying the loop rule. You can see we have a different rule for batteries and resistors, but really it's just thinking about the same thing, the idea of voltage drops and which way I'm analyzing the circuit. So you will notice if, for the batteries, if my loop direction is such that I'm going from negative to positive across the battery, that's the same thing as stepping up in potential or voltage. So we're going to write in our equation a positive change in potential. If you're going from positive to negative, it's like I'm stepping down the battery, and we're going to put in a negative change in potential. Okay? So this is true for batteries no matter what direction the current's flowing or anything. Just consider, am I analyzing from negative to positive or positive to negative? That's the difference between a negative or a positive potential difference. However, for resistors, I have to consider whether I'm analyzing in the same direction as the current or in the opposite direction as the current. So if I were to pretend that, I don't know, current is flowing down my arm in this direction, okay, and maybe the watch is a resistor, and it's causing a potential difference, okay? If I decide to analyze this way so that I'm going against the current, well then that's the same thing as stepping up in potential because I'm going to a higher level. It's like I'm going against the waterfall, okay, going opposite the voltage drop. But if my analysis is in this direction with the current, that's a drop in potential because I'm going with the waterfall. That'll be represented by using Ohm's law. So we'll either write a positive IR, which is a voltage, or a negative IR, depending on whether our analysis is with the current or against the current. Okay? So to start that, I need to pick some loops in our circuit, and I'm going to draw those in. And for consistency's sake, I'm going to start all of them at the top right. And I'm going to say that loop 1 is going to kind of go around this part. Yeah, I know maybe that's confusing, but I don't want to draw on top of the circuit itself. So we're going to go around that top box in a clockwise direction. For loop 2, I'm going to go down here and start at the top right and work our way around like this. That'll be loop 2. And just for good measure, I'm going to do 3 of these and start all the way up there and go wee around like that. That'll be loop 3. So let's start with loop number 1. Starting at this point in the circuit, we're going to work our way around like this. This is our loop direction or our direction of analysis. I feel like we need like music that plays as we're moving along the circuit waiting for something to happen because like as I go from here to here, like nothing's happened yet. I'm waiting to run into something so I can put something in my equation. So can someone like sing music while the pointer moves? You people are all sad. Jeopardy, that was too easy. We need something else. I feel like, is anybody these days, is it even still on TV? Watch The Price is Right. Is that still on TV? Game show, you know? Some confused faces out there. Like, when I was a child, I don't know what, during the summer, I watched it every day. I was a sad little kid, apparently. I guess I didn't want to go outside. I don't know, but there was something fun about trying to figure out the answers to the little games. Does the box of macaroni and cheese cost $2.69 or $3.84? I had no idea. I'd never shopped for macaroni and cheese, but still, it was fun somehow. I remember there's like one little game where there's like a little thing on I don't know, it's like a mountain climber or something, I think. And like you're supposed to like push the button when you think the mountain climber gets to the right price. And it was like yodeling or something or other, you're like waiting for it to get to the thing and you make it stop. So I need yodeling. Go. This is the most depressing everything. I'm just sad and disappointed at all of you. So I arrived at the battery. Congratulations. Notice I'm on the negative side of the battery, and I'm going to go across to the positive side. That's a positive increase in potential of 45 volts as I go that way. And now that we've passed the battery, we're going to keep going, and we run into this resistor, and we're traversing the resistor from right to left, which you'll notice is in the same direction as the current. So it's like we're going downstream as we go entirely across these two resistors. Downstream means a drop in potential difference. So I can write this as minus 1 times I3 minus 40 times I3. Resistance times the current. And then we've arrived at the junction on that left side, and we're going to start our way up. I made my own music, and it was sad too. But at least we had something, right? And then we arrive at this 30 ohm resistor, and we're going in the direction of the I1 current. So that's still downstream. So I'm going to write that as minus 30 times I1. And then since I'm back at where I started, we're going to say that that's equal to 0. Those ups and downs have to add to give me 0 change in potential. And of course, we can combine a couple of things here. We could write this as 45 minus 41 I3 minus 30 I1 equals 0, and then we have a second equation we could use. Good? It's not bad, right? You love it, and you want to sing songs while you do these problems. At home, around your roommates, who will think you're a little ridiculous. That will be my legacy. You will look ridiculous around your friends. Yeah, maybe it's just me that'll look ridiculous. So let's go to the bottom loop. We're starting in the top right corner. I'm going to do this one faster, okay? So keep in mind, let me explain it first. We're going around this bottom part of the circuit opposite to the direction of I2. So that means I'm going upstream. We're going to have an increase in voltage, and then an increase in voltage, and then notice the battery. This is a drop in voltage as we go around that bottom part of the loop. So let's quickly write that down. Let's see. We've got plus 20 times I2 plus 1 times I2, and then negative 80 for the battery. Which puts us at this point, and then we get to this middle part, okay? For the middle, this time we're going from left to right, so we're going upstream against I3. So I'm going to have an increase in potential, an increase in potential, and then I'm going from positive to negative across the battery, which is a decrease in potential of 45 volts. So we could write that as plus 40 I3 plus 1 I3 minus 45, and then I'm back where I started, so that equals 0. And let's combine a few terms. Let's see, it looks like I've got 21 I2 plus 41 I3 minus 125 equals 0. Technically, we have enough equations right now to solve the system of equations for the unknowns, but let's do one more loop for fun. So all the way around the outside, we've actually done both of these parts. We're sort of putting together, combining parts of the other two equations. So you should be able to recognize that we get, 20, I can't write with a laser pointer, 20 I2 plus 1 I2 minus 80 minus 30 I1, and it looks like I'm back to where I started, so that equals 0. Combining terms, 21 I2 minus 30 I1 minus 80 equals 0, ... Yay, we have equations. If you look back on that previous slide, it just says solve the system of equations for the unknowns. Sometimes you'll have problems where it's not a system. Maybe it's just a couple of quick substitutions that don't really involve anything more detailed. Maybe it's not even a system and you can directly solve for some stuff. Maybe it's even more complicated than that. I don't care what approach you use to solve the system. Just keep in mind you won't have a calculator on the exam. So make sure that you know a technique such that you can get to an answer. If you want to practice, I'm going to tell you what these three currents are. So I1 is, interestingly, I got negative 0.85 amps. So it's actually traveling the opposite direction there. I2 is 2.6 amps, and I3 is 1.75 amps. Solve that system of equations, maybe both manually and with a calculator, and just confirm the results to make sure that you are able to do that. Does anybody have questions? Let's see. As promised, I said we would come back to this example problem. I'm going to try not to dwell on it. I'd like to get through it kind of quickly and then go on to finish up the remaining things in chapter 26 and hopefully get the first part of chapter 27 done. We'll see how things go depending on how much you want to slow things down by asking questions. I don't know, you're always free to ask questions, or maybe I'll just get long-winded on something and it'll take the rest of the class. Who knows? Could go either way. So in this problem, it asks how much energy is lost due to joule heating, which is a term we haven't used, in resistor R2 over a period of 15 minutes. You can simply think of this as basically an energy loss. As the current passes through the resistor, the collisions and such in there are going to heat the resistor up and some energy is going to go away. That's what we're trying to find. So if I can find the rate of energy loss and multiply that by the time, we can find what we're looking for. The rate of energy loss is just the power. You might remember that power is energy over time. So we're going to try to find P2 and multiply that by the time, and that's going to give me the energy lost by resistor 2 in the amount of time that we're using. Let's see. So if I want to find the power, I need to find the current through resistor 2 because the power is I squared R. So I squared R times T should give me the energy loss in resistor 2. Sound good? Okay. So let's see. Phone is ringing. I wonder who this could be. Seattle, Washington. Should we just answer it and find out? I can't. I'm not going to answer it in here. Although the last time I got a call from Seattle was Amazon wanting to deliver something. And I was just like, blah. And then my package didn't get delivered and life was sad. So things could be sad later. Who knows? So we're trying to find this E2. So we're going to have to work our way through in order to find the amount of current that's passing through resistor 2 in order to solve the problem. So let's start by simplifying the circuit by reducing it down to one equivalent resistance. So I'm going to start by finding REQ, the equivalent resistance for this circuit. Can anyone point out a relationship between two resistors that seems pretty apparent to you? Are any two that are in series or parallel? I hear 4 and 3 are in what? Series. I like that. So R3 and R4 are in series. So we could find R34, which is just going to be R3 plus R4. And you can look above into the block of data that's there, and you can see that there are two resistances listed in kilo ohms. I'm going to go ahead and convert that over, and then we've got 3,200 ohms for R34. Also, don't forget, when resistors are in series, they have the same current passing through them. So just as a means of review and also to keep track of what's happening as we work through the problem, the current that's passing through this combination 3-4 is the same as the current that would be passing through either resistor 3 or resistor 4 separately. Same amount of current when resistors are in series. So we have combined those two at this point, and if I wanted to, perhaps I could just redraw the circuit really quick. Something like this is where we stand now. So we've got R1, R2, and R34. What's another relationship of two resistors? R2 and R34 are in parallel. Why not R1? It's in series with the parallel combination. If you wanted to look at how the conductors are laid out, R1 doesn't share the same potential difference as R2 and R34. So we can't say that it's in parallel as well. So let's put another line here and say that R2 and R34 are in parallel. So we could find the combination of those, which we might call R234, which is going to be 1 over R2 T2. Every time. It just floats into my head. Every time I say R2, D2. It's just kind of there. I can't help it. R1 over R2, D2, plus 1 over R34 is 1 over R234. Okay? So put those together, solve for R234, and you should get, let's see, I've got this number here somewhere, 1672. And don't forget that resistors in parallel have the same potential difference across them, so I'm going to make a little note to myself that V234 is the same as the potential difference across 2 is the same as the potential difference across the 3-4 combination. And now we just have R1 and then this combination of R234, let's see, and our voltage source that looks something like that. And those are clearly in series with each other. So once we've combined those, we have R1234 or REQ, however you want to think about that. So let's see, going up to the top here, R1 and R234 are in series. So we can say that R1234, which is the same as REQ, is R1 plus R234. So REQ is 2242 ohms. And now we've simplified everything down to just one equivalent resistance. Let me make one more note here that the current through 1 is the same as the current through 2, 3, 4 because they are in series. And since that's all that's in the circuit at this point, that is the same as just I, the total current that's in the circuit. And now we have a resistor REQ and a voltage source. And whatever current leaves here is just the current I. Okay? So once we've simplified things down this far, I can find that total current using Ohm's law. So we could say that the potential difference is equal to I times REQ. So I is going to be V over REQ. And they told us at the top that V, or the source voltage as they've labeled it, which is 15 divided by 2242, gives me the current, which is 0.0067 amps. And then we can sort of work our way backwards to find the exact amount of current that's passing through resistor 2. So to start that process, don't forget that you can use Ohm's law with the whole circuit. You can use it with any individual resistor. You can use it with any portion of the circuit, as long as the V, the I, and the R you're talking about are consistently talking about the same thing. So let's start by saying that V234 is equal to I234 times R234. And from just above, this total current that we just found is the same as the current that's passing through the 2-3-4 combination. So let's take that and put that in there. And also R234 is hiding over here. So we can find V234, and it is 11.2 volts. And then we'll hop over to this little statement, that V234 is the same as the potential difference across just 2. So now I can write that V2 is equal to I2 times R2. You didn't want to finish it that time, huh? R2. Yeah. See, even if I'm not saying it, there should be the echo like in your brain anytime R and 2 are said together. Am I the only one this happens to? No, there's 2 others. Fantastic. We are the weird ones, apparently. Great. I'm excited about that. Sigh. You other people are sad. Just so very sad. I'm just curious. Anyone in here who's never seen a Star Wars movie? I ache just a little bit. I hurt. We should just stop right now. The remainder of this course is just watching Star Wars movies. Why not? Don't I wish? So let's see. We can use this to solve for I2. So I2 is V2 over R2. Thank you. That wasn't really an echo, though. Just D2. Can't just say it outright. It has to be haunting just a little bit. So let's see. 11.2 goes here, and R2 is from above all the way up there, 3,500 kiloohms. So you should get that the current through resistor 2 is 0.0032 amps, which we can finally use all the way up here at the top. So plug in that value in amps, square it, plug in the resistance, make sure it's in ohms, change the time over to seconds, so not 15 minutes, but convert that to seconds by multiplying by 60, and then you can find E2 to be 32 joules over that period of time. Fun. Easy enough, right? You all don't look too worried. Question over there, yeah. You can go that route, yeah. Since you have the choice between the two, you might find with some circuits just sort of going straight at the circuit with Ohm's law is easier. Sometimes it's easier to use Kirchhoff. Take your choice. Anybody else? No. So let's see. Look at this. I squeezed that all into one slide. We don't even need this, do we? So we'll do this and draw a little face up here. Why not? There we go. I don't know what that became. It scares me a little bit, and hopefully it'll scare those who look at the slides later. Let's see. So we did all this stuff with Kirchhoff's rules. We'll jump over that. We finished that with an example. This problem is a little bit too easy to spend any time on. You can see there's 8 amps in the middle, and then there's this split on the other side of 2 amps and something else. It's pretty obvious the other branch must be 6 amps. So let's move on from that to something a little more fun. I'll let you read this and see what you think. And also admire those light bulbs. Those beautiful, beautiful light bulbs. Look at them. Wow. How's life back here? Doing okay? Yeah? You both look mad. Are you mad at me? What did I do to you? Are you mad at each other? No? Do you even know each other? Maybe a little bit? Okay, fine. I'll just keep moving. You do look mad at me, though. I'm scared now. No one else looks mad. The light bulbs in the circuit are identical. When we close the switch, what happens? Did anybody bring ice cream? Would have melted before you got here. Anybody mad over on this side? Nobody looks too mad. Some of you look focused. That's good, I guess. Focused on ignoring me. I understand how this works. Yeah. 1, 2, 3, 4, 5. Vote. Go. I saw at least 3 different votes there. How about we go with number 5? Number 5. Why? An exotic argument. I'm scared. I can't argue with that. Yeah. Anybody want to add to it? Yeah. The switch doesn't have any resistance, so it doesn't change any current. Roughly speaking, yeah. Anybody want to disagree with the answer and fight for one of the others? Thinking well, why would you do that after we've already said number 5 is the answer? Yeah.
So I was just thinking back to elementary school science when we did a series circuit and there were a bunch of light bulbs in a line.
Yeah.
The ones at the start of the circuit was brighter than the ones at the end.
Okay.
So that's what I was just thinking. And once you close the switch, then they all have the same power.
Okay. I like it, though. Yeah, thank you. Anybody else? Yeah. None of them are actually light bulbs. Well, I got to say, I can't really argue with that answer because, wow. I can say this, though. At least it looks like they were good to maintain a connection there everywhere. There's no gaps, so the conductor is connected everywhere. That makes me a little happy. One way to think about this, I'm just going to pick a point here at the bottom and say that this is V equals 0. Pick any number you want. And we could say that as we go this direction, 12 volts are added, such that this is at positive 12 volts. And if I keep going this way, I'm now at plus 24. Oop, don't know why I put a point there. And then since the resistors of the light bulbs are equal, and also I have to go around the loop and get back to V equals 0, well then this must be negative 12 volts, and this must be negative 12 volts, which means that this point is at the exact same potential as the other side. Even if I make the connection, there's no potential difference. There's no reason for anything to flow that way, even with the conductor being connected. Okay? Maybe using that answer, you can come up with a very nice answer here. I think you're probably arriving at the answer that you did on the last slide, which would be nothing's going to happen through that center branch. Why? Again, the resistors are equal. You can imagine there's the same potential drop across each of the resistors. So maybe this is minus V sub R, and this is minus V sub R, which leaves A and B at the exact same potential. And then you'd lose the remaining part of the voltage getting back after the other two resistors. So we could say that VAB, that potential difference, is 0, so nothing flows across that central branch, right? And then this. It's going to take a little bit of trial and error. One of those equations is correct. Which one is it? And I should quickly determine for myself which one it is. Might be useful, yeah? Mm-hmm. Who's got a vote? One person has a vote. Is that a vote or is that a question? It'd be a strange way to ask a question with one finger. I have a question. It seems to me if you follow a loop around that looks like this, you'll come up with equation 3. Yeah? You have a question? If it doesn't have any resistance, wouldn't it follow the path of least resistance? The problem is it's still going to meet resistance either way. So if you thought about this path compared to, say, a path that does this, it's still the same. So it's still not going to choose to go that route, right? Everyone good with the answer here? Does that look right? Yeah.
If we're going in that loop, we got 2 as like a potential gain.
Mm-hmm.
Why is, if it's going with it, why is it before the potential drop?
Because we're going from the positive side to the negative side there. And it doesn't matter which way the current's flowing. We always just say if we step this way across the battery, it's positive. If we step that way, it's negative. Okay? Anyone else with a question for Mr. Kirchhoff? No? Okay. I want to get to the next slide, and there's not a whole lot here that's serious. I'm just going to refer you to your textbook for this one. There you go. There's like a paragraph like this big. Go read it, and you know everything you need to know about series and parallel voltages or EMFs, all right? Instead, I want to present one other DC circuit, one other direct current circuit that has a little bit more going on. The current is, in general, going to flow the same direction in that it's not oscillating back and forth. Once it's going a particular direction, it's going to stay that way until I make some significant change in the circuit. So it's still direct current. Problem is, it's a dynamic circuit where some things are changing with time. So if I have a resistor and a capacitor in a circuit, an RC circuit, one of each of those or any parallel or series combination of those, but just some combination of resistors and capacitors, we're going to have a source voltage and a total resistance and a total capacitance that are being held constant. You can think of those as the physical things in the circuit that I built it with. I took a voltage source, a battery, or some combination thereof, and some resistors and capacitors, and those are going to stay constant. However, the current in the circuit and also the charge on the capacitor and the potential difference across the capacitor are going to be changing with time. So for the first time when we're dealing with a circuit, if you were asked what's the current, you have to follow that up with when, because at every point in time there's going to be a different value for the current in the circuit. This is a more in-depth look at what we did with capacitors before when we described how they were being charged. And we went through that whole process of saying that you could think of positives as leaving this side of the battery and going over here and beginning to build up on the capacitor, which repels positive charges from the other side. And then after some period of time, you get a maximum amount of positive and negative charge separation, and the whole circuit sort of stops. Now we're going to zoom in on that process and think about the entire charging process. Instead of just saying this happens and you end up in this state, we're going to look at the process of that occurring. So notice state A over here is at t less than 0, which is a little weird, I guess. Think of this as before we begin to charge the capacitor, and you will notice that the switch in that circuit is open. Nothing is happening. At t equals 0, we're going to close the switch and begin starting the timer that tracks how long we've been charging the capacitor for. So now t is greater than 0, the switch is closed, things are happening, and those three variables at the bottom are beginning to change, okay? So if we just think about how this should occur, we're starting with no charge on the capacitor, no potential difference on the capacitor, and those are going to start to grow. As I put more and more charge on the plates, it gets more and more difficult to put more charge on the plates because there's a back repulsive force. So you might imagine that we start with a process that's occurring quickly, and then it's going to start to slow down as time goes on, okay? So we can describe this with some graphs as well as, let's see where I want to put this, as well as some equations. If we were to graph the charge on the capacitor, so QC, as a function of time, it would start off like this and then approach some maximum value. And Q max is going to be equal to C times V, the capacitance times the supplied potential difference. We can write this function, Q as a function of time is equal to the maximum charge times 1 minus e to the minus t over tau, where tau is one of the most simple, elegant things all semester because the name of this thing is the equation, and I kind of like that. It's the RC time constant, and it's simply equal to RC. You got to love that. I think all equations should be named with what's inside them. That would get a little lengthy. Especially if I just look at that one equation right there at the bottom of the slide. I don't think we want to do that at all. So tau is the RC time constant for this function. And the R and C here are just one resistor and one capacitance. If you have parallel or series combinations, you'll have to make sure that you're using the equivalent resistance and capacitance in the circuit. You have the exact same thing basically for the potential difference across the capacitor. Like so, it's going towards some Vmax. Both of these are a function of time. And we could write that as V sub c as a function of time is equal to V max times 1 minus e to the minus t over tau. Same exact time constant based on the physical characteristics of the equation of the circuit that's been built. These are the things that are growing. We're charging the capacitor. The charging properties start off rapidly at the start and then begin to fall off in their rate as time proceeds. The current in the circuit goes the other way. Since we're starting off rapidly charging, it's really easy to put the initial charges onto the plates. We start with a maximum amount of current, and then as it gets harder and harder to push more charges there, the current's going to begin to fade away toward zero. So we could say that the current as a function of time looks something more like that, where this is I max. It's just equal to V over R in the circuit, and it's fading away to zero a little more asymptotically than I drew it there. And this is going to be I as a function of time is equal to I max times e to the minus t over tau. Which describes that decreasing exponential as the current fades away. We can look at that graph and see that a couple of things are happening. At this initial point in time, as soon as you make the connection, charges are free to go. And the entire circuit sort of behaves like there's a wire connected across the capacitor. In other words, it's not behaving like there's a gap there. Charges are freely going. It's behaving like the capacitor is a short circuit instead of a device. So we could say that C acts like a short circuit. And then as I wait long enough, eventually the current is going to go to zero. And at that point, the capacitor behaves exactly like what it is. It is a physical break in the circuit where there is no conductor or conducting path across. So we could say at that point, the capacitor acts like an open circuit. Once it fills up, everything stops. Nothing flows in the circuit at all. That is the process of charging the capacitor. So you've got an exponential growth or a decreasing exponential growth for the charge and the voltage, and then you have a current that starts high and then fades away. On the other hand, looky here, we have these graphs on the next slide, don't we? Didn't need to draw them. Get rid of that. Discharging the capacitor. We're going to start with a maximum amount of charge separation on the capacitor plates at t less than 0, and then we're going to make the connection that would allow charge to leave the plates. You'll notice there is no voltage source in this. You could think of the capacitor as sort of a temporary dying source of voltage in the circuit. And also notice that the positive side is going to try to reconnect with the negative. So we're going to get current flow that's going in that direction, opposite from the way it originally charged. And this time, well, everything is temporary, right? Once the charge has sort of reunited with the other side and everything is neutralized, it's over. It's dead. It's done. There's nothing left to do unless I go back and connect it to a source of potential to recharge the capacitor. So in this case, we could just draw, say, just one graph. And let's say that this is the current, and this is the voltage across the capacitor, and the charge on the capacitor. And in all cases, it's doing something that looks like that. So it starts at some maximum value, and then degrades off to 0. We're going to say that this top value is the value V naught or Q naught or I naught, which is how much it started with at the beginning. So these are the starting values after charging. So we charge to some maximum. It may not even be all the way full. When we start discharging, these are the maximum values for the second part of the process. In all cases here, we could say that we have the exact same function. So we could write VC is V naught e to the minus t over tau. I is I naught e to the minus t over tau. And QC is Q naught e to the minus t over tau. Just keep in mind the T here is the time that it's been discharging. So you're not still counting from all the way at the beginning. T is how long since we connected the circuit without the source of potential being available. So T is the discharging time. Okay. Thoughts, questions, complaints, anything right here? It starts at the maximum that it can for the amount of potential that's on the capacitor. So think about the process of charging, first of all, and the current. Charges you can think of as, if you want to, as being pushed from the battery through the circuit over. They start really easily flowing because there's nothing on the capacitor plates. And then eventually they get full. So we're going from lots of current to no current at all. As soon as we start discharging the capacitor, those charges want to get off the capacitor. They're repelled by each other and attracted to the negative side. So we start with the highest possible repulsion, which leads to the highest current. And then as there's less and less charge on the plates, there's less and less of a reason for more charges to leave. So there's less of a current and desire for those to move. Okay? Anybody else? This is some slide to have up in the interim. Anybody? Anything? All right. So let's see. What I want to do, blank example problem slides. We're not going to do that. We're not going to do that. And we're not going to, well, actually, there's scary things happening here. Maybe we should do this. I don't know. Apparently, blow drying your hair is very scary. So don't do that. Of course, there's a little bit more that's going on there. I'm going to not talk about this. I trust that these are things that you're pretty aware of. You can avoid being shocked. Let's see. We're going to skip that and instead go to this last little bit, which ties in with this week's lab. And I'll be somewhat brief about this. I just want you to be aware of how some of these things that you're using in lab is working. And that is the process of measuring current and voltage and resistance and how these devices work. So, of course, the ammeter is the thing that measured amps. It is measuring current. The key is that you have to put an ammeter such that the current you want to measure actually passes through the ammeter itself. It's like you have to take the meter and set it in the river of current and let it experience what's happening, if you want to think about it that way. So if I want to know the current that's flowing at that location in the circuit, I literally have to disconnect the circuit and build in the ammeter at that point so that whatever current is there actually passes through. The issue is that once I do that, you might think like, oh, this is a different circuit all of a sudden. I had one thing, and now I took another device and stuck it in the circuit. I've changed it. My circuit isn't what it was, so even though I wanted to know that current, now it can't be the same as what it was before. The key is that the ammeter has to have really, 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 really low resistance. In other words, we're trying to change the circuit without actually changing the circuit. If it has really, really low resistance compared to all the other resistances in the circuit, then the idea is that it's not really affecting the current in any measurable way, and you don't have to worry about it, okay? On the other hand, if I want to measure voltage or potential difference, well, clearly it's measuring volts, so we call that a voltmeter. This time, instead of putting it in the circuit, I think of a voltmeter as being something that sits on the outside, and it's measuring the difference between two different points that are in the circuit. It wants to know a difference in potential. The way that this is done is by connecting it in parallel with the circuit element that I want to know the potential difference across. So the key here is, well, if I wanted to know something about this potential difference, if I put something else in parallel, have I just changed the potential difference? Well, not if, in this case, we have an item that has really, 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 really high resistance. If you think about it, if all of a sudden I put this in parallel and I have current that might flow this way or might flow this way, but this has really, 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 really high resistance, that's what high resistance looks like, then nothing's going to flow that way, and really I haven't changed the circuit at all. So for ammeters, we want low resistance. For voltmeters, we want ridiculously high resistance. And then it doesn't really change the circuit and what we're trying to measure. All right? Finally, with resistance, we use the ohm meter. And the ohm meter is interesting in that it's sort of a little Ohm's law device in and of itself. It's got a little bit more going on than the other meters do. And the key is to make sure that the resistor that you're trying to find the resistance of isn't actually in use, that there's no current passing through it, and ideally that it's not even connected to the circuit at all. Because inside the ohm meter is a battery of its own and a high-resolution ammeter that completes a circuit when you connect it across the resistor you're trying to find the resistance of. So you might think of this as, I don't know, something that looks like this. Let's say this is the box of the ohm meter. Here we go, ohm meter. That's too many. I needed an H in there somewhere. OH meter. That's too many M's, it looks like. I don't know anymore. So this is the ohm meter box. Yay, there it is. Let's say it's got two places you can make a connection out here to a resistance. So it looks something like that. So you're going to pass a current through there. So maybe you have something that looks like this, such that there's a battery inside. And then inside of this, there is an ammeter that's going to measure how much current is passing through. And also, ideally, I know exactly how much potential difference I'm applying. So it's completing its own little circuit inside the device, and then it can say that V over I is equal to whatever that external resistance is. So ohm meter, more's happening, keep it out of the circuit, and everything works a little bit better. Okay? Questions about any of those three? Yeah. It does stay the same in a parallel circuit. And yet, even if the potential difference is the same, we could make some changes if all of a sudden we're putting something in there that would allow some current to go through that second path. To minimize the amount of impact, it's important that none of my current goes that way in the case of a voltmeter. Anyone else? That's chapter 26. Should we celebrate with ice cream? Yes. So while we've been talking, what I did was, I spoke to Ben & Jerry's using my brain, and they are now bringing ice cream if it worked. I failed. Apparently I can't do that. Well, it was worth a try. Why not? Chapter 27. We really should celebrate, though. Chapter 26 is done.